Today we're going to continue with the technologies. Last time we stopped at this slide. So we said fuel cells are technologies that are considered to be one of renewable energy technologies. And it is so because it uses hydrogen. It can use the fuel, but it can use hydrogen. The problem with renewable energy resources are intermittent. Their nature is intermittency. Maybe some of you can elaborate on this. What do you mean by intermittent resource?
Continuous at the same time.
Exactly. So they are not continuous. If you look at power systems, it's not like let's say fuel supply, or it's not like communication systems. The balance between supply and demand need to be maintained in real time. So I cannot call X customer and say, excuse me, can you please turn off your air conditioner for 2 minutes and then tell we are just to serve customer. We cannot do like that. And wind and solar are not calling us and saying, oh, excuse me, there will be a cloud passing by in a few minutes, so please I will be reducing my output. So this is not the case. So we need to deal with this intermittency, variability, and also forecasting error. So this is the problem. So one way to deal with that is that excess energy can be used actually to produce hydrogen. This is one way, and store energy in a form of hydrogen, and then we can run the fuel cell. So that's why normally fuel cells are considered one of the renewable energy resources, or let's say technologies that use renewable energy. Although currently we are using just hydrocarbon fuels. Okay. The process is simple, as discussed before. So we inject hydrogen on the anode side, and we inject oxygen on the cathode side. So the positive side, we inject the fuel, if you like. The negative side, we inject air. In this case, air is containing oxygen. And then the ions of hydrogen will be allowed to pass through this electrolyte, this separation between the two electrodes. And then electrons will have to recombine with their ions on the other side, going through the load. So going through let's say our load, which is the energy consuming device. Okay. And this way you can actually produce electricity and also water. You will produce also water. You can increase the efficiency of this system by using that hot water, the energy content in that hot water. There are some, so it produces without combustion. Prototype machines make electricity by combining hydrogen ions with the oxygens, with the electrons that pass through the load. The current is brought to the size. We covered that. The voltage is limited to the size of the plate, so we can have let's say the same stuff with the fuel with the PV system. So we can have parallel and series connection to increase the voltage and to increase also the current. These are some examples. We covered this one. There is an issue. There are some issues. The first one is that hydrogen is a volatile gas, requires special storage and transportation. We don't have these facilities, so normally we need to upgrade, let's say, the existing storage facilities to deal with hydrogen. Hydrogen cannot be found free in nature, so it can be generated using a reformer from hydrocarbons, or it can be using renewable energy resources. The excess energy can be used to produce hydrogen. Efficiency is much higher than the efficiency of the internal combustion engines. The efficiency is from 26 to 40%. We need to remember that normally internal combustion engines are up to 22%. The engines of the cars, for example. So it's much more efficient. If you use it combined heat power, it can be reaching to about 80. So it can depends on the application itself. Before going to geothermal energy, I want just to show you a small clip that describes the hydrogen. So this is, you can see the flow here. So we have hydrogen, it is separated. There is a catalyst in this anode. Ions can pass through the electrolyte, and then they will recombine with the electrons, and then they will generate water and electricity. So this is it's a simple procedure. It's very useful. It's like a battery. There is no, you generate electricity without having rotation machines. Okay. Now another important source of actually renewable energy is geothermal energy, the energy content, the heat content in the underground water, in the underground actually. These are some statistics. By 2011, 24 countries are using actually these technologies. We have power plants that uses geothermal energy. Majority of this capacity is located in few countries: United States, the Philippines, Indonesia, Mexico, and then some other countries. Iceland is one of the important countries that uses actually, it's a pioneer. Although the capacity is smaller, but because of the size of the system, this is the largest, let's say, if you look at the contribution of the geothermal, the largest contribution will be in Iceland. Okay. So it's about 18% from the energy, 26% from the installed capacity. Sorry, 26% for the Iceland and 18% for the Philippines. How can we harvest this energy? Basically, we have hot magma. So the rocks close to the hot magma are really hot. So if we have rainwater descending closer to these rocks, they will be heated up. Okay. Once heated up, they will migrate up. They migrate upwards, and then they can be trapped in a cavity. And then if we have access to that cavity, if we can drill that cavity, we can actually get that hot water, and then we can use it. This is just one technology. This is just one procedure. We have different actually procedures to harvest that energy. This is one procedure. You have the reservoir that contains that hot water, and you allow that hot water to come to this chamber, the mist eliminator, to separate the mist from the water, and then that dry steam will be directed to a turbine. Okay, this is one technology. And then to close the cycle, you need to have a cooling tower. You need to have a cooling medium. So this should be located close to rivers and so on. You can even use that water to heat for other heating purposes. This is one technology, or this is one way of utilizing this energy. Another way is you don't actually allow the steam that is generated, the direct steam from the reservoir, to be in the turbine, because steam turbines have leaks, and these are it might be containing odors and bad smells, and also some maybe hazardous material. So normally you will have a heat exchanger. So instead of having mist eliminator, you have a heat exchanger, and then you can use that to generate steam. So different technology. But the idea is you need to drill to the reservoir and then to extract that energy, and then later you can use it either directly or indirectly, but using a heat exchanger. Okay. This is one, and I think this is in Italy. I'm not sure. This is one of the plants. Some aspects that the site is, we should have sites that are close to the surface. Magma is very deep, so we should have sites that are accessible. It's not always the case. Underground reservoirs are often surrounded by very hard rocks, so drilling technologies, it will be expensive if you have very hard rocks. Geothermal fluid can cause water pollution due to the presence of some gas and metal in the reservoir, so these are some impacts. Geothermal fields could also produce carbon dioxide, but at much lower levels than the natural gas power plant. So these are some. Processing the reservoir fluid produce objectable odors. So this is also a concern when we think about the application of this energy. Ocean energy is another energy that can be harvested. There are different types of actually ways or different forms of this energy. This is just one of them. We can have tidal, and then you can use the low tide and the high tide using turbines, barrages and turbines. This is actually the main stream business in harvesting ocean energy. So most of the projects are using this idea. The other one is wave. There is a project in UK using wave energy. So the wave itself. This is high tide and low tide due to the moon and ocean thermal energy. I am not aware of any project actually using the thermal energy from the thermal difference between the higher, let's say, the water on the surface and the water down deep the ocean. So the water normally deep the ocean is much colder than the water on the surface. So this can be used also to produce some energy. Osmotic, the difference in the salinity of the water. The tidal systems, this is a very famous system. This is one in France. It was in 1966, still working. So this system is still working. This is the barrage system, where you use the high tide and the low tide with also turbines. So additional projects are expected in Canada, Russia, China. So this is the capacity in 2001. But this is very famous. This is one of the oldest projects using this idea. By 2010, only tidal barrage systems have achieved commercial scale. Others were, I don't have the updated numbers now, but still I'm not aware of any technology other than the barrage and the waves. Other things are just research and maybe demonstration projects. This is the idea. So during high tide, this is what we call the lagoon side. So the side of the let's say of the land. Okay. If this is the sea, and this is just water. So this is the sea, and this is the small, let's say small bay. You can actually make a barrage here. So you can make a barrage here. You can make that dam here, and then in that dam, during high tide, the sea level will increase, then water will flow inside this, let's say, lagoon, and then you can produce some energy. Okay, you can just communicate that to rotational energy and then to electrical energy. At low tide periods, you can allow water to fly again to the other side. So this is actually the procedure of these systems. This system. There are some issues. Dams can slow the flow of water. They can stimulate the growth of red tide organism. So this is an issue. They might cause some environmental problems. Maybe you have heard about this problem. It occurs periodically in Oman. Tidal energy is expensive method unless you really have a good location. I can't think of, for example, Masandam to be a good location for such systems because they have a lot of lagoons and mountains. Energy can only be generated when the current is strong. So maybe I would say more than 70% of the time you will not be able to generate anything because the flow will be smaller. You need really to have some difference so that to have strong flow. So it's not generated every time. You need to have some difference between the seaside and the lagoon side, and vice versa to have enough energy. Okay. Another way to harvest ocean energy is wave energy. This is just an example. There was a project by some students a few years ago. We participated with that project. I remember in some conferences. It's another technology, but there are different ideas to harvest wave energy. In that project, basically what students did is they have like a small system with some legs. So these are different legs, a box with different legs. Okay, and these legs will have some anchor here. So you'll have some anchors here, and these are floating. So with the wave, this can have a motion, and then they can rotate the generator. So this is one idea. The idea mentioned here is you have a chamber, and when the wave is rising, then the pressure, the air will be pressurized here. You have here one valve, and here you have another valve. These are just one-way valve. So when you are pushing the air, it cannot escape from this side because this is just to allow the air in. So the air have to go this way, and then it have to go through a turbine, and this will rotate the turbine. When it is getting down, then the air will come from another valve, going again through the turbine, and then going from the other valve. So you will have this, let's say this turbine will have a continuous direction. So it will be in one direction. So this is one way of also harvesting wave energy. Another way is to have these things here, ocean worms sometimes they're called. This project is in the UK. It was implemented, it was commissioned, but they stopped it after a short period of time. I met one guy in a conference in Spain, and they said that they stopped it because of the high maintenance. So, corrosion and salty water. So it was, but still it was experimented. So this is one project. This is one project that uses the ocean energy. And basically what you have, this is just another picture. Okay. So basically what you have is that you have different sections. When the wave is coming, it will maybe elevate one section, the other section will be down. So that motion, so you have, I will take another pen, okay, not to confuse the board. Okay. So we have, let's say, these two sections. We have two sections. We are having it a wave coming. So the wave will hit the first one. So we have it will increase it here, and then later it will burst with this one. So this will be there. So with this motion, you can generate actually some rotational, kinetic, some rotational motion, and then you convert it to electricity. This is the idea there. Okay. I'm going to show you a video that has these actually waves.
Despite the fact that the oceans cover 70% of the planet's surface, we've only begun to tap them directly as an energy source. But these marine powerhouses may one day unlock the door to clean, limitless energy. Hydroelectric power was the great renewable energy source of the 20th century, and it will continue to provide gigawatts of power. But with most of the world's rivers already dammed, the future of hydropower will come from the sea. Of the various technologies to capture the ocean's energy, a tidal barrage is the closest in design to traditional hydropower. The barrage is essentially a dam, collecting water from high tide until there's sufficient potential energy for power generation, then forcing the water through turbines when released during low tide. The world's largest and oldest tidal barrage at Lorence, France, began producing power in 1966. Today, it still powers 240,000 homes. A more recent technology known as tidal stream power uses propeller-like turbines to capture the kinetic energy of underwater currents.
And that's one that we could do in all manner of places, because the tidal flow, of course, takes place everywhere on Earth. And harvesting those could be done quite well, and doesn't even have to be at the surface. The issue, though, is that the marine environment's pretty tough to deal with. There's corrosion, parts being banged back and forth. Often the costs of managing those in terms of repairs can be quite large. But we're seeing new work on that.
Much of the work is taking place in the British Isles, where companies such as Marine Current Turbines are thinking big, sinking massive pilings into the ocean floor and letting the turbines do their work.
And the amount of energy you get out of a turbine is proportional directly to the density of the fluid that flows back and forth. And so a water turbine has several hundred times the power of an air turbine.
Wave power is an even newer technology. Yet it may hold the most promise of all, since wave power can be captured anywhere on the ocean. In this design, a 450-foot chain of pipes, connected by hinged joints, sits semi-submerged on the ocean. Each motion of the waves is resisted by hydraulic rams located in the hinges. This action pumps high-pressure oil through hydraulic motors, which drive electrical generators. Electrical transmission lines also keep the floating power plant tethered to the ocean floor. A Scottish company, Ocean Power Delivery, has installed a successful 2.5 megawatt wave farm off the coast of Portugal. A wave farm occupying less than half a square mile of ocean would generate 30 megawatts of power, or enough for 20,000 British homes. 472 square miles of ocean could power each of the United Kingdom's 24.5 million households. Each region of the Earth has its own renewable sources.
So this is actually, that's it. Just the remaining is just different ways to harvest ocean energy. But the available commercial one is the barrage. Thermal energy. Also, people are thinking to harvest the difference in temperature between deep ocean water and the shallow water. So the water close to the surface, because this is much colder than this one. If there is a temperature difference, then this temperature difference can be used actually to evaporate ammonia, for example. And that ammonia can be expanded in a turbine. So this is also one idea. I'm not aware of any project, but this is an idea. People are thinking of, if the difference is let's say, big enough, then we can actually drive a steam turbine. Then the steam is not water, it's not the water vapor, it's maybe ammonia, because in a heat exchanger. Biomass energy. This is very common in many countries. We don't have such one in Oman, but it's actually just to burn the garbage. You just need to burn the garbage. Instead of just dumping the garbage, you can get some money from that garbage. The biomass consists of garbage, agricultural products, and tree crops. So if you have this, if you have this garbage, you burn it. It's like you are burning coal. The same story. So you have some heat from burning this garbage. You use boilers to boil that water to get steam, and the steam is directed into a steam turbine, and then you can rotate a generator. So this is one way of harvesting the energy from the biomass. Of course, there are some hazardous material that we should take care of. So we need to have filters to filter the light ash and the heavy ash, and then we need to be careful also with the emissions. Okay, so this is one way. Incineration produces heavy metal and dioxin. These are some concerns about this method. Heavy metals is mixed with ash, but is posing a serious pollutants to water. So this is dioxin is the most dangerous element. So dioxin exists actually in these ashes. So we need to be careful with that. Are you aware of any projects similar to this in Oman? Have you heard about BIA? Okay, so BIA, Oman, there is a holding company for environmental services owned by the government. And they have a plan to have this project close to Parka. It's not finalized yet, but I attended some meetings regarding this. And it's not to produce electricity. Actually, it's to produce water. Okay, because to produce water, you need to have energy. Okay, in their feasibility studies, they say they found that it's more economical to produce water. The benefit will be much more compared to if you are producing electricity. So their plan is to have a plant, this plant close to Parka. They were looking for approvals and so on. This was 6 months ago. I don't know. I did not contact them at that time. So things are maybe there is one plant in Qatar. I think there is one plant in Qatar that uses this. What's the main motivation of this one? Do you know what's the main motivation of having these plants in cities? It's not energy.
Reducing the garbage.
Reducing the garbage, because actually it's expensive. The land is expensive. So these landfills that you put garbage in is very expensive. So to reduce the size of that garbage, you can just burn it. You can reduce the weight. Maybe it will be just 1% of the initial size. And then this way you can save lands, you can sell that land, or you can make use of the land for other purposes. Okay. Do you have questions? So now we are going to start a new topic. For some of you this is new, maybe. So the current structure of power systems in Oman. Renewable energy, we hope that it will be contributing to the power system, to the electric energy in Oman. Therefore, it's important to understand the current status. What's the current status of power systems in Oman, of the structure of the market? We talk about restructuring of the sector, the companies that works in this market, demand characteristics, electricity sector economics, future of electricity sector. So these are the points that I am planning to cover. Some history. Previously we had who was responsible, what entity was responsible for giving us what electricity. Do you remember? If you are living in Suhar, for example, Majan is giving you electricity, right? Anybody from Suhar? From Suhar? So in Al-Batina, Majan will be giving you electricity, right? So before Majan, who was responsible?
Government?
Government, what entity in the government? What ministry? So earlier we had a ministry called Ministry of Electricity, Housing and Water. So it deals with the three tasks: electricity, housing and water. So this was the last ministry that was handling actually electricity. We had the Ministry of Electricity, Ministry of, the names were changing, but the last one before it was this activity was removed from the ministry was Ministry of Electricity, Housing and Water. Therefore, sometimes you will see MHEW. So in the pipelines and the maybe old transformers, you will see MHEW, Ministry of Electricity, Housing and Water. So that's their assets actually. But there was an idea to restructure and privatize the sector. The Council of Ministers approved this idea, approved this in '99. It was implemented later, so the idea was to separate between facility of generation, transmission and distribution. Maybe I'll go.
Use the volume. Use the volume from there.
Okay. This way?
Yeah.
This is for the computer. Okay. So maybe I'll go this way. Okay. So the idea is to separate the different activities, and to separate activity for electricity and water desalination, assign them to different companies. So we need to have, the idea is to have different companies. I don't want to go through this because this will be repeated later. And we need to establish an independent authority to regulate these activities. So a regulator. So this was the idea in '99, and this was actually implemented by a royal decree in 2004. So in 2004, that ministry disappeared. So that Ministry of Electricity and Housing and Water disappeared, and we had a new structure in the country, in the business of electricity and water. So this structure, this law has a 155 articles. You can download the PDF version of that royal decree from the Ministry of Legal Affairs website. There is an Arabic and there is also an English translation in the Authority of Electricity Regulation website. So this royal decree is you can have a look at that. And there was a period, there was a transition period. So on the 1st of May, this was the Minister of National Economy implemented the transfer scheme whereby electricity and regulated water assets, liabilities and staff of this ministry transferred to successive companies. And we have different companies. These are just some of the companies. You can see here Majan company, Majan electricity company. So North Al-Batina, Buraymi, Dhahira. So this is Majan. You have here Mazoon. So people living in South Al-Batina, Dakhliya, Sharqiya, both South and North. These are, you will be dealing with Mazoon. Mazoon is authorized to give you electricity, nobody else. In Muscat government, Muscat electricity company from UDC. In close to Salalah area, it's Dufar Board company, and all other areas that are not covered by these distribution companies are for rural area company, rural area electricity company. شركة كهرباء المناطق الريفية. So these are the most of their business actually in Masanda. About 40% of their business is in Masanda. Okay. in these systems, renewable energy currently is negligible. There is no really renewable energy utilization. You can see some characteristics. This is the peak load that was recorded in 2014, 5,000, about 5 gigawatt. That was the peak load that we are concerned about. And for those who are not from ECE, maybe for those who are from ECE, they are familiar with this figure, but for those who are not from ECE, this is general background of the system. Normally you have generation facilities to generate electricity, and then you step up the voltage, so these are normally 10 to 15 kilovolt, the output here 10 to 15 kilovolt, and then you step up the voltage at higher voltages, high voltage up to 1 million volts sometimes. Okay, you transfer it over these high voltage lines, and then close to customers you just step it down. And there was a common question, right, when we discussed why we need to step up this voltage. People from ECE, they know that it's to reduce losses. To have this station and to have that station, this is just step down transformer. This will cost about 7 million Omani riyals each station. So why we are investing that much money? We don't need here 220 kilovolt. We just need the medium voltage that was here. So why we are investing in these stations? To reduce losses, basically. So to reduce losses, when we are transferring power over long distances, we need these step-up transformers. And to power our houses, we cannot. Our TV, our mobile, they cannot handle the kilovolt. We need to have safe values of voltage. Therefore, we need to step it down. So these are basically the idea of stepping up and stepping down the voltage. These are the voltage levels that exist in the main interconnected system. So we have 220 kilovolt, 132 kilovolt. These are the transmission levels. And we have 33, 11, 415. These are kilovolts. This is 415 volts. These are distribution voltage levels. So these are the ones that are. Now, this part here is owned by a different company than this part. So previously, before 2005, everything was owned by the Ministry of Electricity, Housing and Water, except some generation facilities. But everything was owned by one entity called Ministry of Electricity, Housing and Water. Nowadays, we have different owners. So for example, this system is owned by different distribution companies, Mazun, Majan, and so on. This system, so that the green part here is owned by Oman Transmission Company, the high voltage operator, the high voltage system, and we have different companies that actually produce it. So these are normally private sectors. And this is the market, this is the current existing market. We have the main interconnected system of Oman. 2 power plants are owned by the government only. The remaining 9 power plants are owned by the private sector. So this is the generation companies. Rosail power plant was owned by the government earlier, but it was sold to the private sector. And then these generation facilities are connected to the transmission system, the high voltage, the 220 and 132 kilovolt, and these transmission companies connected to the other companies, Majan, Mazun, and Muscat. Okay. This model is called the single buyer model. It's a single buyer model. You are not allowed to sell electricity. The only one who can sell and buy electricity is OPWP, Oman Water and Power Procurement Company. Okay. So OPWP would actually buy electricity from the generation companies here, and then they will sell it to distribution companies. Okay. So this is the situation. So the flow of money, let's say it will be from Muscat, Majan, Mazun company. They need to have the money. They give it back to OPWP, and OPWP will give it back to the generation companies. It's a single buyer model, 100% natural gas based generation facilities. So 100% of this system is natural gas. We have other systems like rural area system and also the far power company. The far power system is similar to the main interconnected system in the north. So the far power company, I'll talk to this later, but the far power company is very similar to the main interconnected system. You have 2 generation companies. you have the transmission company, and you have also one distribution company. So what will happen to the electricity? Electricity will come from generation facilities, it will go to the transmission system, and then it will go to the distribution, and then to you or to us. Okay. Money will go the other way around. So this company will collect money from customers, and then they will pay to OPWP, and then OPWP will pay to the to generation facilities. It's a single buyer model, natural gas facility that is connected. And you can see these are the some capacities that we have, but it's not really owned by the system, but they can contribute. Now, what is our demand? What is the characteristics of our demand? This is one figure that will show you some characteristics. So this figure will show you the peak electricity demand versus the month. So you can see that, for example, we have peak during summer, right? June, July, we have peak, right? This is one characteristics. So in some let's say, let's take the latest data. So let's say in January and December, we have the peak is about 220. Let's say 2,200 megawatt. This is the peak. But in June, the peak is close to 4,700 megawatt. So there's a big difference between let's say the winter months and the summer months. This is one thing. Keep this in mind, because you'll be installing capacity. Whether you are using that capacity or you are not using that capacity, you have to pay for the debt. You have to pay for the loans for that investment. Okay, this is one thing. So utilization will not be good. And in terms of assets utilization, you will have like 60 cars. You will use 60 cars one day in a year, but in the remaining day, maybe you will be using only 40. Sometimes you will be using only 5 cars. So the remaining will be just idle. And despite this, you have to pay the loans for the remaining cars. So this is one characteristic of this. Another characteristics is that you see these are different years. You see the different years here. So different years from 2006 and 2013. The consumption is actually increasing. So demand is increasing. Demand is increasing. This is good, maybe. Maybe this is bad. I don't know. We have growth in the country. I know that for example, for the United States, they have their economy is growing for the past 10 years. Maybe it's a bit, but it's still growing. But there was no added capacity. It's just an efficient use of resources. So this might not be a good sign. Okay, this is inefficient use of resources. We're adding capacity at a very high rate because of the increase in demand. This is one thing. Demand is growing, 80% increase in peak demand between 2006 and 2013. 9% annual increase in peak demand. Just to let you know how much investment to cope with this demand, it's about 100 million Omani riyals investment per year. So per year we just need to, this is not for the fuel, this is just for the wires, transformers and generators. On average we have 100 million Omani riyals as a more investment. Now, if this demand is increasing, how can we supply the demand? So you see this is the latest report from OPWP, from the procurement, Oman Water and Board Procurement Company. They are the company that is responsible for planning for capacity, for planning for generation. So how can we satisfy this demand? This is the demand, the blue line, let's say the expected demand. This is the low scenario demand. This is the high scenario demand. So if we have very good let's say economy and increase in demand, this will be the scenario. If this is if we have low expectation, then this will be the demand. How can we cover this demand? You can see here the green bars. So the green bars is actually the existing capacity of generation facility. These are the existing capacities, and you can see that actually we are with the normal curve, with the normal expected curve, we are actually below the demand. So we need to have investment. So we need to have more capacity starting from 2016, and this is getting even worse. So how can we satisfy that demand? Three options are there. Contract extensions. So the private companies that generate power actually are having contracts. These contracts are expired, so we just renew the contract. This is one option. Renew some contracts. The other option, construct new power plants. Ebri, Suhar. So Ebri and Suhar. This is the plan. These are the plan to power plants. Reserved from other companies. So you can also borrow from Emirates. You can borrow from PDO and so on. GCC countries. So these are the options. Natural gas resources. I thought this is just one comment that I wanted to highlight now. There was a plan to have a power plant in Duqm. Maybe you've heard about that. 10 years ago, there was a plan to have a coal power plant in Duqm, and it was phased. It was not implemented. There was a lot of opposition to that idea. Now, Royal Area Company or OPWB approached actually the Minister of Oil and Gas to secure natural gas for that plant, but they said we don't have enough natural gas, it's already committed. So natural gas resources are committed. We need to think of this seriously. It's already committed, so the reserve that we have is already, the capacity is already known that this percentage will go to this part, this percentage will go to this power plant, this percentage will be exported through the LNG, this percentage will be for, let's say, for the industries and so on. So natural gas resources are committed. It might be over-committed even. Now, demand characteristics. What type of demand do we have? I mean, this can be even known from this scale. What type of demand? Is it industrial demand? Is it residential demand? Normally, industrial demand will work 24 hours all the season. So normally, it has a flat profile. But demand that will fluctuate with the weather, that's just air conditioners. So this is air conditioners. Actually, about 80% of the peak demand is thought to be air conditioners. 80% of peak demand is just air conditioners. So we need to think also of that when deciding what technology to use to improve the system. So these are some statistics. Most of electricity consumption is residential, not industrial. The source is Authority of Electricity and Water, Authority of Electricity Regulation. So you can see that for the main system it's about 50%. For Salalah system it's less than that. For Raiko it's again about 50%. About 50% residential, and some other percentage commercial, and also commercial and governmental is very similar to residential. So air conditioners basically. This is another demand is seasonal. About 80% is used for air conditioning. This is the peak demand. So about 80% of our peak demand is just for the air conditioners. And this is very important. So we need to think of policies, for example, to reduce this consumption. We need to think of how can we make air conditioners efficient maybe, or how can we make our houses, our buildings airtight, not to lose that air conditioners. Maybe you have seen the classes also. Sometimes you have it's very cold, and you just open the door to let that energy escape go away. That's just crazy, right? Just burn gas and then let that energy go away. This is the correlation between the temperature and the demand. So you can see in, for example, in hot summer months, these are the average temperatures. You have actually high demand. In winter months, you have low demand. So there is a high correlation between the demand and also the temperature. And you can see here different correlations. The same thing is happening actually in Salalah. You know, this is Salalah power system. Salalah power system in demand. You can see the months, so January till December, and you can see the demand for different years. But just to consider 1 year, just consider 2013. You can see the demand is increasing. January is slow, February is slow. It's higher because we have higher temperatures. You can see the temperatures here. So temperatures are getting higher, demand is getting higher. In July, August, September, it's actually lower. It's lower, although Kharif. So we have a season actually there. Despite the fact there are many people going to Salalah consuming a lot of electricity, maybe in heating waters for the band, unused swimming pools and so on, but still the demand is much lower than the other ones. And this will give us an indication that it's just air conditioning. So our demand is actually air conditioners, so we need to think of that. This is one reason why we are having this unbundling business, mate. So one reason, this is just a characteristic of the losses, because you said why we are going to this business of unbundling, separating the activities. Instead of having vertically integrated system, one entity will take care of everything. Now we are having unbundling, we're having distribution, we are having generation, we are having transmission, just to take care of losses. This is one thing. And you can see here the brief restructuring. What was the losses? This is the percentage of losses from the total generated power, and this is the years. So you can see that losses were actually increasing, and just before the restructuring, it was about 25%. So about 1/4 of energy that was produced, we don't know where that energy is going to. Okay, so these are the losses. Okay, yeah. So after restructuring, Muscat take care of Muscat, for example. Transmission company take care of losses in transmission systems, and so on. So different companies will take care of different components of losses. This was decreases. Losses is an important thing because you are generating energy, but that energy is lost somehow. You don't recover that energy. It might be in I square R, it might be in the conductor itself, it might be theft. People can steal electricity, right? Measuring, calibration, and so on. So it is getting down, and there are targets. So every year there is a target that is set by the Authority of Electricity Regulation. If these companies are meeting the target, then somebody will get bonus. Not everybody, somebody will get bonus. If they are not meeting if they are not reducing the losses, then they will not get that money. Okay. So this is one characteristic, and you can see these are just some targets. They are not receiving. Actually, they are not getting the targets. None of them. These are in 2012. So this is one important thing. These are the losses also in rural area companies. Sometimes it's higher, sometimes, but still it's much lower than the previous years. Okay. Now, when we are talking about losses, it contains two parts, two components. One of them is the technical losses. Technical losses that engineers can calculate, I square R. So you have a conductor. That conductor is not a superconductor, it's just made of copper. So when there is a current flowing in that conductor, you will have losses, right? Heat. The conductors will be heated up, that heat will just go to the air. So this is technical losses. Non-technical losses, theft. People can have jumper, just the meter is, sometimes they have a magnet, sometimes there are different techniques to steal electricity, right? So this was a problem. So theft, meter tampering, meter is not calibrated. One way to reduce the losses is to replace meters. So old meters will go away and new meters will come. New meters are very sensitive. Now we have digital meters, we have prepaid meters. It's sensitive to theft. It can send signal when there is the theft, and the company can come immediately and investigate. And old meters were not calibrated. So with the new meters, you measure actually the actual consumption. So normally some bills will go higher than normally. Because it's not because the new meters are not good, it's because the old meters was really not calibrated long time ago. So at every few years you need to have these meters calibrated to have the proper readings. So this is one way also to reduce losses. Okay. Tomorrow we are going to start here with the economics, and I need you to think of the bill that you are paying. Is it too much or is it too high? Is it too low or too high? Maybe some people they say it's too high. Some people might say it's too low. Okay, think of that next time. We'll start with this, inshallah. Thank you for your attention.